Good morning everyone. This is Bhumika from IIA PCMB. Today I will be giving a presentation on the chapter Dual Nature of Radiation and Matter. Let's begin with the introduction. Here are certain discoveries by a few scientists. Maxwell's equations of electromagnetism and Hertz's experiments established the wave nature of light. Roentgen discovered X-rays in 1895. The cathode rays were discovered in 1870 by William Crookes, who later, in 1879, suggested that these rays consisted of streams of fast-moving negatively charged particles. Last but not the least, J.J. Thomson discovered electrons in the year 1897. Let's move on to the next slide. Electron emission. The process of emission of electrons from the surface of a metal is called electron emission. Different types of electron emission. There are three different types of electron emission. The first one being thermionic emission. The second one is field emission. And the third one is photoelectric emission. Let's go through them one by one. Thermionic emission is the process of emission of free electrons from the metal surface by heating. Field emission is the process of emission of free electrons from the metal surface by applying suitable electric field. Photoelectric emission is the process of emission of free electrons from the metal surface when light of suitable frequency is incident on it. There are three observations in this chapter which we will be going through today. So the first one is Hertz observation. As I am explaining, you all can go through the points. The first point is when ultraviolet radiations begin to fall on the arc lamp on the emitter plate, the intensity of sparks across the detector lobe increases. So when the ultraviolet radiations, when they fall on the emitter plate, the electrons present on the metal surface absorb the radiations and acquire sufficient energy in order to escape from the metal surface into the surrounding space. And then when these electrons reach the detector lobe, the intensity of sparks increases. The second one is Lenard's observation. As we saw in the first observation, that is Hertz observation, ultraviolet radiations from the arc lamp fell on the emitter plate. Here in Lenard's observation, ultraviolet radiations will be falling on the emitter plate of an evacuated glass tube enclosing two electrodes. So when the ultraviolet radiations are falling on the evacuated glass tube, current flows to the circuit. As soon as the ultraviolet radiations stop, the current flow to the circuit also stops. When ultraviolet radiations fall on the emitter plate, electrons are emitted and these electrons are attracted towards the collector plate. Flow of these electrons towards the collector plate resulted in the current which is seen in the external circuit. The third one is Hall's observation. As we saw in the first observation, Hertz observation, the ultraviolet radiations from arc lamp fell on the emitter plate. In our second observation, Lenard's observation, the ultraviolet radiations fell on the emitter plate of an evacuated glass tube. Here, the ultraviolet radiations fall on the negatively charged zinc plate. So when the ultraviolet radiations fall on the negatively charged zinc plate, they lose electrons and become neutral. And when they continue to fall on the zinc plate, they lose more electrons and hence become positively charged. Therefore, Hall's concluded that negatively charged particles were ejected out from the zinc plate under the action of UV rays. Let's begin with the experiment. This is an experimental setup of photoelectric effect. So, you all can go through the points as I am explaining as well as look into the picture. A our first point is about the apparatus. So, the apparatus consists of an evacuated glass tube having a photosensitive plate C and a metal plate A, which in turn is connected to a battery in order to maintain the potential difference of the two plates, that is, metal plate A and photosensitive plate C. Our second point is when a monochromatic source of light from the source passes through the quartz window, the quartz window permits ultraviolet light to pass through it, that is, to pass through the quartz window and in turn to fall on the photosensitive plate C. So, our third point is about the photoelectrons which were emitted from the photosensitive plate C. So, when the ultraviolet radiations pass through the source with the help of a quartz window, the ultraviolet radiations fell on the photosensitive plate C. So, this photosensitive plate C emitted photoelectrons which is in turn collected by the metal plate A, which caused the flow of electric current in the circuit, and when this reached the collection plate, they were measured through an ammeter. Our fourth point revolves around the commutator. The commutator basically is used to change the polarity between the two plates. The current can be either increased or decreased by varying the potential of the collector plate C. The intensity and frequency of the incident light can also be varied. We have three graphs. These are about the effects of the intensity of light, potential and frequency on photoelectric current. So, our first graph is about the effect of intensity of light on photoelectric current. Since photoelectric current is directly proportional to the intensity of light, the graph is a straight line and the number of photoelectrons emitted per second is also directly proportional to the intensity of incident radiation. Our second graph is the effect of potential on photoelectric current. So, there are 3 points in this graph. Our first point is when the positive potential of the anode increases, photoelectric current also increases. This is also called as saturation current. Our second point is if the negative potential of the anode is increased, photoelectric current decreases and hence becomes zero, which is called as cutoff potential. So, it's easy to remember, that is, if the positive potential of the anode is increased, photoelectric current also increases. If the negative potential of the anode increases, photoelectric current decreases. There are chances of it that it may also become zero. Therefore, it is called as cutoff potential, and when it is connected to the positive potential of the anode, it is called as saturation current. The last point is stopping potential does not change with intensity, but saturation current increases with intensity. That's what we saw in the first point. If the positive potential of the anode is increased, photoelectric current also increases. This is called saturation current. This is our third graph. This is about the effect of frequency of incident radiations on stopping potential. So, here are 2 points to be remembered. So, in the first point, when the intensity of incident radiations is kept constant, the frequency has a variation. And in the second point, when saturation current is kept constant, stopping potential has a variation. So let's look into the conclusion. Saturation current is independent of frequency, but stopping potential is dependent of frequency. The reason why stopping potential is dependent on frequency is because in the two cases also, in the first case frequency has a variation, and in the second case stopping potential has a variation. So stopping potential is dependent of frequency. Saturation current is independent because frequency has a variation, whereas saturation current is kept constant. We have come to an end. So I actually took the points from our notes as well as from the textbook. I hope you all like my presentation. Thank you.